Hello and welcome to the second video in my Intro to CFD series. In this video I will be showing you how to get started and set up and run your CFD simulation in ANSYS Fluent. The version I will be using today will be ANSYS Fluent 18.0. In this version they include some pretty nice features, so I highly recommend using this version over the previous versions. And with that, let's get started. Picking up where we left off yesterday, here we have our NX model. As you can see, we have the air boundary made. Here's our workbench project, and we will import this now using the importer. Next, we will add a Fluent Flow module to this system. And in this, we're going to start off by creating our mesh for this file. As you can see over here, we are going to be using the CFD physics and just sticking with the default settings. You can also do this by component systems and just use the mesh from this, as well as doing the Fluent from this. If you want higher customizability, this is the route to go, although they're about the same. For this tutorial, we'll stick around with the default options. Once the mesh loads, we can get started. And now that we have our object loaded, we can get started on generating the mesh. Let's just look at it for a second. And it looks pretty well. First, we need to start creating our inlet and outlets. You do this by creating a name selection in the mesher. So here we are calling the front side the inlet, just so when we import it into the mesher, it knows. Next, we're going to create the boundary walls, and we'll just call this the walls. And finally, we have to include symmetry, and so we just call this symmetry. And next, we do the outlet, and we just call this the outlet once again. And with all these defined, when we import this into the solver, it'll automatically recognize these name selections and apply your conditions for you. However, this should do well. As you can see, we do have all our faces defined, and we might actually want to include the bottom part as for the wall as well. However, since we have a moving part and a stationary part, the outer wall boundary conditions will be provided with no slip going at 80 meters per second, and the interior boundary will be applied with slip. So we have to separate these. So we have our pod and the wall, we have the inlet, we have the outlet, and we have symmetry. And once we bring this into the solver, it'll automatically recognize these different name selections and apply the appropriate boundary conditions. So now we're just going to change the relevance down a little bit to make our mesh a tiny bit finer. And here we have our mesh. Now, as you can see, it meshed all of it for us. It did pretty well. We might want to refine this just a little bit, or we can do different options. As you can see, you can play around with each of these on your own time. For now, I'll just do one set of refinement on this. And now that it's finished meshing, let's look at how it looks. It looks pretty well, very fine on our shell, which we expected to have quite high gradients on this, so it's good. However, this bottom part has quite big edges on it, so we're going to just increase the relevance a little bit more and generate our mesh. And once this finishes, we'll see what it looks like. And you can also check the quality, and right now it's aiming for a target quality of 0.9, which is relatively high for the skewness. You can also change through and look at all the different kinds of quality mesh metrics you have. Skewness is the last one. As you can see, here's our average, max, and standard deviation. For skewness, you want this to be as low as possible. And here's our mesh. It's not the best mesh ever, however, we're going to increase our relevance some more and see if we can make the skewness a little bit lower. And our mesh is finally finished. So let's look at how it looks. As you can see, the bottom part has a lot finer mesh, which is good, and the body itself has a good mesh. So next we're going to close out of this and open up our setup. and we have to update our project so it loads the mesh from the previous step. So all this is going to do is going to remesh it and then import it into the next step. And now that that has finished, we are going to just run this. We're going to do a parallel mode with, let's do 16 processors and 1 GPU, since we do have a graphics card in this computer that I'd like to use, as well as 16 core processor, virtual cores of course. And we can leave the rest of the options, and once we have it open, it's going to start its script and start loading everything in. Alright, now that it's all loaded, we'll check our mesh. It looks like our mesh is good. And as you can see, here it is. The controls are a bit different from meshing, however, you'll get used to them. So as you can see, here's our domain. So next, we're going to set the model that we're going to be using, since there's going to be a high Reynolds number in this. We're going to be using K omega just to see how it works. K epsilon is a pretty standard choice, however, and I highly recommend using that one for any beginners. For any turbulent models, of course. If it's not turbulent, you can leave this as laminar. Now that we're done with models, we can look at our fluids. So as our solid is aluminum, that should be okay. Let's look at it for a second. It's aluminum, solid. You can change this if you want. However, for this tutorial, I'll probably leave it as a default. There's a bunch of different materials you can choose, so feel free to pick one that best suits your needs. And we'll just leave that at the default once again. So we'll close this, we'll look at our fluid. It's set to air, that should be okay. The cell zone conditions, you can also leave this as the default. Boundary conditions, as I said before, this was imported from our mesh. So the inlet's already set to the correct side, it's the frontier. If I can get to it, there we go. So we're going to just set the reference frame as absolute. We're going to give it a magnitude and direction in the components. So gauge pressure we'll leave at 0. That's just atmospheric pressure. Next, we'll look at the x, y, and z velocity. If you look at the side, you can tell that our x velocity is going down the tube, so we'll set that to minus 80 from 80 meters per second down the tube. Turbulence, we'll just look at this. That should be okay. We'll leave that at the default. Next, we'll look at the symmetry, and that actually applied to the boundary, so we're fine. We'll look at our wall next. This is a moving wall, moving at 80 meters per second, minus 80 meters per second in the x direction, absolute, and it's a constant, and we should be able to leave that as is. And so this will match our inlet velocity. Next, if we look at the pod wall, this is going to be a stationary wall with no slip. And outlet pressure, this is set to gauge pressure, and that should be fine as well. And so that should be all of our things that we need. I'm not quite sure what the interior is, however, it's there. For our reference values, we'll have to change these based on our pod size and dimensions. And so now I'm going to get started on creating the force reports. So if you look through all these, you can see there's a variety of different options. However, we're just going to do a force. And you can see there's a bunch of them. You can explore these to fit your needs as you want. But like I said, just going to do a quick force report on the drag. And so we're going to rename this to be drag, the CD, drag coefficient, and we're going to set this to be on the pod. And we're not going to average it, we're just going to leave this at the defaults, hit OK. Next, we're going to make a new one and lift. And you can view these once you're in your computation. These will tell you what your CD and CL are if your reference values are set properly. And so projected area, I couldn't get to work here. That's just this area up here. However, that's not what I wanted. I wanted the projected area, and that's not quite the projected area. Next, I'm just going to get just the overall drag force, and as well as the drag coefficient. These are going to be these are what the solver will calculate, and then they calculate CD and CL from the reference values in this. So I want to just see what these values are. And so there we go. That is our lift. Hit OK, and we should be good now. Hit OK. Next, you can see monitors for your convergence and whatnot, and other calculation activities like autosave, you can set there. Before you just run right in and run the calculation, you're going to want to initialize it, as well as some reference values. So like I said before, the reference values you need to set in order to get your CL and CD computed accurately. I cannot get this to work, calculate the pod. As you can see, it doesn't really calculate anything, so that's fine. We're just going to go straight into initialization, do a hybrid initialization. The default, it's going to say it's not been saved. That's okay, we didn't really do anything, and now it's initialized. Next, we can run our calculation if we wish. However, I'm going to solve or save this workbench first in case something goes wrong. I don't want to lose all our data. So I'm just going to call this shell FEA, shell CFD. And then just today's date, 2017, 4/25. And once this saves, we can go ahead and run our simulation. It's just saving our setup container right now and writing the different files. And you can see all these files. They stored in a secondary folder with all these files. You can go and look at this if you want. It can become quite large if you save every single run that you do ever. So next, we're just going to set our number of iterations to 1 and calculate. This is going to be very inaccurate and is not going to be good values. They'll be close though, within a few orders of magnitude. And you can continue just hitting this, and you can see already that our residuals dropped quite significantly, or they did drop. So let's just set this to be a lot higher. Let's see, 100, and use these settings for all the calculations, and now it'll run 100 of these iterations. And each iteration is going to continue to try to improve on its error. As you can see, the error has dropped quite a bit already. And it's going to continue dropping for a while. You can run this 4,000 times, however, probably around 250 iterations, you're going to stop decreasing your error and you're just going to stagnate. And at that point, you're just wasting your time. As you can see, the error is already going up a little bit on a few of them, but it's still going down for the most part. So I'm going to leave this run for all 100 iterations. Alright, we're almost done to 100 iterations. I just skipped forward there for a bit. And we are done. So hit OK. And let's look at some of the plots. So here is where you can plot your data that you told in your report definitions to plot. So that's all these values up here. Your CD, CL, drag, lift, all those things are what are printed. You can also just click on them and hit compute, and you can see our CD is 682, which is very clearly not right. Our drag is 438, and this is right. This is the actual. So we need to calculate our projected area. If we go here, we can calculate our projected area and select our pod and hit compute, and this will give us the area of our pod in the X direction. And so this is going to be used to calculate CD, so we need to have this value. So we're just going to copy this, close out of this, and go to reference values and set it here. I recommend doing this before you run it. However, you can do it afterwards and just rerun it a few more times, and you can get your updated values. And the rest of these look good. So that will conclude our video. And once again, you can just run this again and get your new values. Thank you for watching. If you like this, hit a like and leave a comment, and I will be producing more videos. Also, click on here to go and watch my previous video where I show you how to set this up in NX. And next video, I will be trying to go over parametric sweeps, where I will show you how to set up a parametric sweep, as well as run hundreds of these different simulations if you so desire. Thank you for watching.